We can start. So welcome to this special edition of the Gardener review meeting. As you might know, we have a schedule of Kubernetes release responsibles. And since the last version 1.32, we have also introduced these special editions here in this round so that the responsibles can share some updates about the releases. Here we typically follow the agenda to look at graduated features, then promotions for features that have been promoted to beta. Then we look at brand new alpha features, and finally on security and what's changing for Gardener. So this time we had Victor, Plum, and Radar being responsible for the 1.33 release. And yeah, let's hear from them what they can share with us.
Yep. Hello, folks. So let me start by sharing my screen. This, and let's start. Okay, so I am audible, right? Yep. We will present today the changes that come with Kubernetes 1.33. As Rafael mentioned, what was graduated, what was promoted from alpha to beta, and new features in alpha. Also, changes in relevant changes in Gardener, some security improvements, API removals, deprecations, and so on. So let's start. As we also presented, as it was mentioned last time during the presentation, we have a new initiative called Gardener Kubernetes Release Responsible, where we had to update the Gardener extensions, bumped the Kubernetes IO and controller runtime libraries, drop support for old versions, and then we had to present all these changes in the review meeting here, or at least, most of them related to Kubernetes 1.33. The name of this Kubernetes release is Octarine. It was released on 23rd of April 2025, and the theme is basically the color of magic, which was inspired by Terry Pratchett's Discord, and it kind of highlights the open source magic that Kubernetes enables across the whole ecosystem, which I think was a nice touch on their side. Okay, so we already went through the agenda a couple of times. As I mentioned, graduation ceremony, beta bloom, fresh off for new releases, security deprecations and removals, and finally what's changing in Gardener. And here I will hand off to Rada, who will talk about features that were graduated from beta.
I'm going.
Sorry about that. Sorry, we had some trouble with the microphones here, so Rada will have to to a new room. We can continue now.
So I'm going to start with sidecar containers, and you all know what sidecar containers actually represent. But basically, prior to this feature, there were technically only application containers, but people would define these so-called sidecar containers, and through documentation, these additional containers were actually referred to as sidecar containers. And for example, they would be used in scenarios where they would be used as additional jobs, or for metric collecting, for log forwarding, for service mesh, and such stuff. We can switch on to the next slide. So here, the one solution they actually introduced was, if you introduce the restart policy. If you can see it on the slide, you would be able to mix the one-time and the long-running support containers in order to use them in an ordered startup solution, so that you can use the sidecar containers as ordered containers and not just in the container section. And that way you would have a shutdown sequence that wouldn't affect pod termination. The next feature gate would be backoff limits per index for index jobs, basically when you run them in parallel and when you run multiple instances of the same job. You have this backoff limit parameter in Kubernetes jobs that would specify the total number of retries. Since sometimes you would have a flake or something similar to that, and that way you would have a more fine-grained backoff limit on a basis for an index job. And you can see in the example in the next slide, you would have like a backoff limit per index, and then you would have a max failed indexes section where if you have basically if one index fails, it's okay, but if more than 5 fail, then the job would be failed. So yeah, as I said earlier, if you have a flake, you can tolerate that. But if it fails like more than half of the time, it would be definitely a fail. Then we introduced the job success. Kubernetes introduced the job success policy. So you know how in the spec we have the completion sections and the completion section, and then there would be some situations where you might want some additional control for deciding whether a job has succeeded. If you want a job to be run with different parameters, for example, in testing and stuff, you might not need all of the simulations to succeed in order for the job to be successful overall. Or maybe if you're doing like a leader worker pattern, maybe you would need the leader to succeed and maybe some of the workers to succeed. You can see it in the next slide. Here you can define rules, for example. Here we have decided that for example purposes, we would say that the 0 index is the leader index, and then from the rest, from 1 to 9, we would want at least 5 to succeed. And that's the minimum required value for the count of successful indexes. Yep. Also something that was introduced, but I don't think it was documented, or someone can correct me on that, on their blog. We found that there was this bound service account token security improvements where they introduced JTI, and this enhancement actually introduced features such as including a unique token identifier and some node information that you can see selected in the screenshot within the tokens, which would actually enable more precise validation and auditing, since you would have more information about the node that made the request. You will have the name, the UID, and stuff. And you can see how with kubectl you can create the token, and that would lead to actually this request with the selected stuff with the additional info. Then something really useful, at least for me personally, the sub-resource support in kubectl, since it's like an older feature gate since 1.27, but still it's really useful for commands like get, patch, edit, apply, and replace. You can use the flag sub-resource and the sub-resource name. And you could get the status, scale, and resize sub-resources. For example, you can see a few runs for an Nginx deployment, like an example deployment. If we get the status, we can see how many of the pods are ready and stuff. You could see if you get the scale, then how many replicas we want, how many are actually available. And you could use it in a patch in order to specify the new count of replicas you would want. Then we have some networking, which is like really exciting. We could allow users to dynamically increase the number of service IPs available by creating new service siders. As you know, we have like a one-to-one relation between IP addresses and services. We can see that through the screenshot to the side, where we are getting the service Kubernetes, and then we get the IP, and then we get the IP address as a resource. Sorry. But then again, we have a one-to-n relation between the service sider and the IP address, which is like basically a map for the IP addresses. And then we would have this thing where we can increase the number of service IPs by creating this new service sider, and then overlapping service siders will be merged in memory. And there was this quote in, I think, the documentation where you can see it in the last bullet. IP address doesn't come from a specific service sider object, but any service sider that includes that IP. So that's nice, and that would be useful in networking. Then another thing that could potentially be useful for networking and other stuff, the NF tables that are used globally. This backend for the kube proxy is now stable, and there is like a new implementation that would improve performance and scalability for the service implementation. So for compatibility reasons, because some Linux nodes can't really update to the requirements for the NF tables, IP tables would remain the default on Linux nodes, but still users who want to switch from the default IP tables to the NF tables in order to make their lives easier should be aware that some features would work slightly different in the NF tables mode, and maybe should read up on it in order to keep it short and simple. Some topology-aware routing with the option for traffic distribution and prefer close value for it. This basically would mean that after this field was added, with the prefer close option, if you set it, this would direct traffic to the nearest available endpoints based on network topology and it being zone aware. So this configuration would enhance performance and cost efficiency by minimizing the interzone and like cross-zone communication. Another feature gate would be the options to reject non-SMT aligned workload. I think most of you guys are familiar with SMT workload. But this feature gate, which is CPU manager policy options, this would prevent workloads from requesting cores that don't consume a full CPU by just rejecting them. For example, you can see it, the orange part, so 05 as an address. It's not used, and this feature would guarantee that no physical core is shared among different containers, which would improve cache efficiency eventually, and it would mitigate the interference with other workloads that can consume resources from the same core And as I said, it would be, for example, useful for cache. The next feature would be defining pod affinity, or essentially anti-affinity, by using match label keys and mismatch label keys. So when a pod is created, the Kube API server will obtain the labels from the pod labels by the keys in match label keys or mismatch label keys, and then it will merge them into the label selector or pod affinity term based on the field. And you can switch on to the next slide so I can show you an example. If you say, you can see the left screenshot, it would be, the key is tenant, the value is tenant A. For the API server, it would be translated directly into the key tenant operator not in values tenant A. But on the left, under mismatch label keys and match expressions, you can see it's defined differently. It would be translated to the Kube API server so that you can make some rules about pod affinity. Then again, we have this other feature, which is considering taints and tolerations when calculating pod topology spread skew. This introduces two new fields, which is node affinity policy and node taint policy, according to the documentation. These fields would allow users to specify whether node affinity rules and taints should be considered when calculating how the pod will be distributed across the nodes. And this enhancement will provide a bit more control over pod placement, where how there's always problems where pods would remain pending due to some unsatisfied constraints, and you could fix that with some calculating pod topology tolerations and taints. Then we have this feature, which is volume populators. It's stable now, and it would allow users to pre-populate volumes with data from sources that aren't just PVC clones or snapshots of volumes. And this mechanism relies on the data source ref, which would be validated by a volume data source validator, which is a special controller, alongside with the new stable custom resource definition named volume populator, which would allow new controllers to register the types of data sources they support. And you can see there's some definitions of a volume populator, and then you can see that it's used in a persistent volume claim under the data source ref in order to be used as a volume populator instead of the most convenient ones, which would be used on a normal basis. And then you have this kind of a bug fix, at least I think for me, which is the always on or persistent volume reclaim policy, because there would be an issue where the PV reclaim policy wouldn't be consistently honored, which could lead to a potential storage resource leak. So the case was if a PV was deleted before the PVC was deleted, then the delete reclaim policy, there was a chance for it not to be executed. And for example, the storage which would be underlying the PV would remain intact, which is not what we want to do with managed Kubernetes. Then we have, I think that's the last feature that's graduated. This would be, again, I think a bug fix, at least in my opinion. It's the recursive read-only mounts, where previously, if you mounted a directory or like a volume with a read-only directory, its subdirectories wouldn't be read-only too. So now it's introduced with, of course, some feature requirements, because it has some dependencies on the kernel and runtimes, that now it will be recursively spread along the tree, the read-only attribute.
Yep. So those were all the graduated features. Now time for the beta bloom, or basically features that graduated from alpha to beta. We start for support for direct service returns in Windows Kube proxy. So basically what this does is that it allows traffic that's routed to load balancer to bypass the load balancer and respond directly to the client. You can see here on the right how much faster basically packets complete one round trip from one pod to a different pod. So this is a great performance improvement for Windows. Then we have dynamic resource allocation with structured parameters now graduating to also beta here. There was a new API actually added, so v1 beta 2, which kind of simplifies the definition for resource claims and devices which you could require for a pod. Basically, it's you can specify here on the right. You can see for the NIC requests, it specifies an exact name for a device. This means that this resource claim requires this device exactly, and nothing else can specify this requirement. And then, for instance, for the GPU, you could have different device claims, which now depends on your sizes of GPU that could be provided to your cluster. Additionally, there was also an improvement in how the rolling update works for instance, daemon sets, which now basically allows when this happens, the resource slice resources to not be recreated, which should greatly speed up rollouts of daemon sets. Then again, DRA goodies, this time for network interfaces. This kind of allows the status of available network interfaces to be reported in the resource claim. And this greatly improves the user experience when you want to check whether a device is available or not. Additionally, there is also information about how the status is reported for a device that is assigned to a particular node. So this could also be used when pods are scheduled to know on which pod to schedule on which node to schedule the pod which requires a particular device. Then we have some kube scheduler improvements. Basically, pods can now be popped off from this backoff queue if the current active queue is empty. Usually what you would have in kube scheduler is that if the active queue was empty, it would wait for some pod to get popped from the backoff queue, then get to the active queue once its backoff time has ended, and then it would get popped from the active queue and get eventually scheduled. With this feature, it can now directly pop stuff from the backoff queue without waiting for them to first get transported to the active queue, which should basically improve performance of kube scheduler greatly in those cases. And there is a new metric added, scheduler queue incoming pods total, which you can use to monitor how frequently popping off from backup queues has occurred. Basically, this would also indicate how much your pods stay in backoff. And one more feature again for the kube scheduler. I think this was presented in the last presentation because it was graduated in 1.32, but now it's enabled by default. Basically, this ensures that higher priority pods get evicted before lower priority ones. And previously there was a blocking API which slowed down scheduling, and now that pods are preempted in parallel, it allows the scheduler to keep working without waiting for preemptions to finish for other pods. Cluster trust bundles. So this is a resource that was added, and it's designed to hold X501 trust anchors, or basically root certificates. So it makes it easier for in-cluster certificate signers to publish and communicate such trust anchors to cluster workloads. Here on the left is a very simple example for a cluster trust bundle. And on the right, you can actually see an example where the cluster trust bundle replaces the currently existing config map, which is deployed in the kube system namespace, which would contain these root certificates for workloads. So yeah, this is kind of the new way that could be used to replace this config map and also ease up deployment of these root certificates. Then we have fine-grained supplemental groups control. So basically this was kind of an issue that was previously present, but maybe not so obvious. When, let's say that you have a Docker file, with the Docker file specifies a group, which is 50,000 a user ID, user Alice with ID 1000. And this is added as a definition in the image. So yeah, this is the user and its group when the image is built. And then you would have a pod that has the following spec with security contexts, which specify the same run as user and group, but it would also add a supplemental groups, which is 60,000. So actually the expectation here would be, at least what the Kubernetes, the authors of the KEP were saying, is that the expectation here would be that the groups inside the image would just be these supplemental groups, which is 60,000. But what actually happens is that, what I mean is that the expectation would be that, the groups are added together, but what would happen is that the groups are overwritten. So to also include these 60,000 supplemental group. And so what was the solution to that? Basically, we now have this supplemental groups policy that has a value of strict, which can be used, which can be added to the security context. And this ensures that the groups are added as what was defined in the security context, and they are not merged with what was also defined in the Docker file. So this kind of prevents unexpected security groups that might be present in a Docker file, and developers don't have to take a look at the Docker file before deploying their workload. So yeah, there is some additional changes, of course, to this to ensure that the container runtime interface implementation supports this feature. There is a container status in the user, in the container that in the pod that will get populated for a particular container with the user ID, group ID, and groups for this container. And then there is also a node status in the node that contains this new feature field, which contains which CRI features are supported. So it would have an indication whether this supplemental group policy is supported or not. And of course, there are changes to the CRI spec, which should allow for these statuses to be propagated. Then we have supporting for mounting images as volumes. This is kind of self-explanatory. Basically, on the right here, you can see that when you define a pod, you can set an OCI, let's name it an OCI volume, and set its data source as an image reference. So this would result in basically mounting this image reference as a file system inside the container. So why would you need this? Most common usages are config files as shareable OCI images. So you do not need to include your config files in your image build. You can share them across basically multiple images or multiple containers like this. You could also package large language model or machine learning weights separate from the image that contains the server, and also share those weights across multiple servers. And from a security point of view, you could build an image that contains private malware signatures and use that from some public malware scanner image that runs inside your container. Just some notes, these volumes are mounted as read-only and no exec, so you can't execute files inside them. Images are only pulled on pod creation, so if you change the image, you have to basically recreate the pod. This has some performance considerations because pods might not get created if your image could not be fetched. And yeah, you need the CRI to also support container, support this feature. So if you're interested, you should check the gap for more details. Supporting for user namespaces within Linux pods. This is a feature which basically adds this new field to the pod spec called host users that is by default either new or true. When you set it to false, it allows a remap of user namespaces within the pod to different user namespaces in the host. Basically, you can see here on the picture on the right, where let's say container ID of 0, a user ID of 0 inside the container would have a user ID that's above 65,536 on the host, and so on. There are ranges reserved for each pod basically on the host, and you can see here also on the right again how these ranges are reserved. Then there is also added this proc mount option for containers. Basically, this to enable it, you need to again use the previous feature and set host users to false. And then you can either decide to specify unmasked or default for proc mount. So default is basically the current behavior. Unmasked means that when the proc file system is mounted inside the container, it will not be masked by the container runtime interface as was done previously. And this allows you to run containers in other unprivileged containers. So basically you can run containers inside pods now without having to flag your containers as privileged. It also allows building containers in pods and so on. So yeah, pretty useful. Just one remark here, both of these features require RunC version 1.2 or above, which sadly is still not present on some operating systems that are supported by Gardner, like Gardner Linux and SUSE. But yeah, hopefully support is gonna come soon. Then there is a new CPU manager policy, which is part of the CPU manager policy beta options, which need to have this feature gate enabled, which is currently enabled by default for them to work. So this feature just adds a new policy option for the CPU manager to distribute CPUs across non-uniform memory access nodes, rather than concentrating them on a single node. Basically, the idea is that if you have, let's say, 2 NUMA nodes, your workload would be spread evenly across them, if that is possible, and so on for more NUMA nodes. This should also improve scheduling for such workloads. Then we have this 0-second sleeps for container pre-stop hooks. Basically, this was container pre-stop hooks were added in KEP 3096, then 3960. And what they allowed you to do is to specify a sleep hook in the pre-stop lifecycle. So for instance, if you wanted your container to, or if you wanted your pod to wait for 10 seconds before it was shut down so that it could drain connections and so on, you could use this to specify it. However, there were some people that actually wanted to be able to specify a sleep of 0 seconds, which was not allowed beforehand. So this is now added in the second KEP that you see above. And some of these use cases are basically users that need to enforce a pre-stop hook on their containers, but they might have some exceptions where a container might not need any pre-stop hooks, so then they could just specify this no-op pre-stop hook to solve these issues. And finally, we have internal tooling for declarative validation of Kubernetes native types. So this is a new tool that is introduced and now graduated to beta, which is called Validation Gen. So this is kind of similar to what is used to generate validations for CRDs. Now, same logic is added to Kubernetes native types. You can see here, for instance, for the replication controller spec, where near the bottoms, we have this field called Kubernetes and specify that minimum is equal to 0. So this basically will generate validation that will ensure that this replica value cannot become less than 0. There is also option to specify validations that should only work for when the request is for a sub-resource of the particular resource. For instance, you can see below here where there is validations for the resize sub-resource or validations for the binding sub-resource. And you could also specify validations for across values, which you can see in the last screenshot here, where basically the current field is limited by the min and max value fields. And here we have a more complete example where it's also shown that you can validate arrays. Lists you could also validate across structures. For instance, here again, a similar example to the previous one with the current field, which is now validated for its mean value in the config struct, but for its max value, it's actually validated to be less than a field inside the limit config struct below. So to actually get this feature working, there are two feature gates. One is called declarative validation, which is enabled by default. The second one is called declarative validation takeover, which is disabled by default. So the default behavior is that both validations actually work. However, declarative validation is not authoritative. So the handwritten validation is actually the one that decides whether a resource is valid or not. However, mismatches are reported between declarative and handwritten validation. So users can, or not users, but developers can use this metric here to decide whether declarative validation is currently functioning properly. And then finally, once there are no mismatches, users or operators can enable this declarative validation takeover feature gate, and this makes all the validation be done by this declarative validation feature. And I think that was it for the beta features. Now I hand over to Victor for the new alpha features.
Yeah, I'll be presenting the new alpha features. We'll be starting with the new configuration file, kubectl, that basically contains kubectl aliases and overrides. And here in the example, we can see an alias about database prods. That is an alias for get pods with labels of what equals database in namespace US2 production. And for the overrides, we can see below, we override the default apply command to use server side and the delete command to use interactive mode. And basically, this config file does not override any cluster credentials or host information. So it basically just specifies user preferences. The next feature gate is configuring the tolerance of HPA. By default, the tolerance is 10%. And with this feature gate, any number can be specified. And basically, this tolerance means how much of deviation of the metric you can tolerate before reacting to issuing autoscale. This is useful when, for example, we have 100 pods, and we want to be reacting to small changes. For example, lowering down this 10%. The next one is configurable container restart delay. Right now, there are example cases where the cost of restart is low, but the impact of creating a new pod is relatively high. So this feature gate allows crash loopback costs to be much more, the restart after a crash loopback cost to be much shorter time. And here in the graph, we can see the difference between today and the new default behavior. And this is enabled by two feature gates: the default crash loopback of decay and the kubelet crash loopback of max, which the max one defines the maximum number of the maximum amount of waiting for the next restart. The next feature gate is custom container stop signals. Basically, prior to it, those custom stop signals needed to be defined in the container image. And if you want to modify that behavior, you needed to build a new image by changing this spec in the image. With this feature gate, you can specify this custom stop signal in the pod spec without the need of rebuilding the image. So here we have multiple DRA enhancements. The first one is taints and tolerations to devices. Example use case is when a device gets overheated and performance starts to degrade. This can be expressed to a taint of the device, which informs the users of potential performance degradation, and via those mechanisms, we give them control to decide whether they should schedule pods on that kind of degraded performance device. This is just an example use case. The next one is basically specifying a list that is a priority preference of the devices that a resource claims. For example, we can order the names of the GPU models that we prefer and even the number. For example, with the highest priority is like you can request the newest GPU. With next priority, you can request one model below the newest one. And with the least priority, you can request two GPUs of even older model. The next change is basically namespace labeled with resource admin access true. Only only users authorized to create resource claims and resource claim templates in that namespace to be able to use the admin access field. This is to prevent change to that field by non-expected users. And the last change is giving the vendors the ability to dynamically create partitions and allocation time to devices, enabling improved resource utilization, because a lot of times one GPU can be shared and partitioned throughout multiple pods. Next slide. Okay, this feature gate basically enforces image pool authentication check for each new set of credentials, regardless of whether the image is already present on the node. Still, optional image allow list could be given and specified that will say what images can be ignored for this feature and won't be repulled. And for non-whitelisted images, the behavior is the following. For the never pull images, those the never pull images, image creation will fail because authentication is required, right? So the never pull images is when you expect the images to be already on the nodes, but this feature enforces to be pulled through an authentication check. And for if not present images, the kubelet will repull the image and ignore the if not present. So the next feature gate is node topology labels that can be used through the downward API. Here we have topology zone, topology region, and topology hostname that are made available via the download API. And we can see in the example where we get the zone label in the volume pod info, and additional node labels can be made available via the downward API using admission webhooks that mutate pods or bindings. The next one is better pod status with generation and observed generation. Basically, this feature introduces observer generation that provide a clear pod status. Prior to this, there is a generation field to the pods, but it was a knob. It didn't do anything. With this one, there is a bug fix that's a field on the pods. There was a race condition between the API server and the kubelets. And the API server and the kubelets, basically there is a race condition, and with this one, with observed generation, introducing observed generation, this solves the race condition. So basically that's it about this feature gate. The next one is the support of split level free cache architecture. Here, previously, before this feature gate, Kubernetes wasn't aware of this architecture. And here in the picture, we can see that the orange workload was spread across multiple cores, not multiple cores, multiple processors with different L3 caches. And with this feature, that workload would be scheduled on a processor that will use the same L3 cache. This improves cache utilization and fixes potential problem caused by noisy neighbors. So the next one is PSI metrics and scheduling improvements. Basically, the PSI stats and metrics using cgroup v2 will be supported, and this is like a barometer that provides warning of pending resource shortages on nodes. And using this, a node can more proactively take steps when major resources start becoming scarce. And I think this is the last feature gate. Basically, secretless image pools with kubelets. It allows workloads to pull images based on their own runtime identity without long-lived and persistent secrets. Yeah, I'll hand over to Plamen.
Yep. So I'll briefly go through the security deprecations and removals in the new version. Basically, there was a CVE fix, which was there was a security issue when dynamic resource allocation feature gate is enabled. There is this node restriction controller that validates resource claim status during pod status updates, but didn't do it during creation. So this allowed the compromised node to create mirror pods and somehow access unauthorized resources. leading to privilege escalation. So this has been fixed in Kubernetes 1.32.6, and after that, and also for Kubernetes 1.33.2. So if you're using DRA, you should probably use these versions. Deprecations, the node info kubeproxy version field has been deprecated. Basically, this is currently still in use by GCP cloud provider 1.28 in 3 and for 1.29 for the external version. And however, it was actually not used at all, or it was kind of presenting false information because there's no way for the kubelet to know what the kubeproxy version is. So there's no way for the kubelet to report the correct kubeproxy version, and there's also no way for the kubelet to know if the kubeproxy container is running on the node that it is responsible for. This feature can be completely disabled with this feature gate, which defaults to true in 1.33. The endpoints API has finally officially been deprecated in the documentation. The goal here is not to delete the endpoints API because there are probably a lot of users that are still using it and that might not completely remove it. The goal though is to, for at least Kubernetes side, to be able to run tests without the endpoints controller and endpoint slice mirroring controller, which is basically responsible for creating endpoints resources from endpoint slices. And yeah, if you want to deprecate and remove endpoints, you could also run KCM without those two controllers. And then for API removals, the Git repo volume driver was completely removed because it had security issues and it was also deprecated for a very, very long time. However, because it still might be used by some users, there is a feature gate which defaults to false currently, and if you want to completely remove it, it should be set to true. And there was also a withdrawal of the host network support for Windows pods. This was originally introduced as an alpha feature in KEP 3.5.03, but it was withdrawn in these corresponding issues. For the first one is related to the code, and the second one related to the removal in the docs. And what's changing in Gardener? Basically with 1.33, we are forbidding the pod eviction timeout field of the kube controller manager. There is a warning currently printed for previous versions, and users that want to continue using a similar feature for clusters that run 1.33 and after that should migrate to using the Kube API server's default not ready toleration seconds and default unreachable toleration seconds fields. There is also the removal of the max empty bulk delete field for the cluster outscaler in the chute. Again, for 1.33, users that still want to use similar functionality should remove this field and start using max scale down parallelism instead. And one more important feature, there is now a deny all network policy that's deployed in the kube system namespace, as you can see here. And for chute owners, they need to either define expected ingress or egress traffic network policies in the kube system namespace if they do use such features, and or alternatively apply a temporary allow all network policy. And for the availability, so support for 1.33 is available from Gardener release 1.122. And the corresponding basic extensions, Alibaba Cloud, OpenStack, and GCP have been adapted to support chute clusters that can run 1.33 with the corresponding versions displayed here, with basically some of them adding also support for the extension itself to be run inside the Kubernetes cluster with subsequent releases. And we expect that similar releases will be done for the AWS and Azure extension soon as well. That was all for the presentation, and now maybe I can briefly show a Kubernetes cluster that I created on GCP that actually runs 1.33. As you can see here, the Kubernetes version is 1.33.2. and it has everything that a vanilla Kubernetes cluster created by Gardener would have. So yeah, I think this is all. We still have maybe 1-2 minutes for questions if there are any. Yeah, thanks for listening through all of this. I know that this release actually had a ton of features that we had to go through. So yeah, thank you.
Thanks to you. Very nice presentation. Thanks for taking the time to prepare all this. So as Plamen said, we have a couple of minutes left for questions. If there is anything, please raise your voice. Nobody? Perfect.
Perfect, yeah.
Then thank you very much again. Thanks for joining and see you next week for the regular review meeting again. Bye-bye.
Thank you.
Thanks.
Bye-bye.
Bye.
Bye.
See you. Bye-bye.